Yeah, hello, I'm Ishan from University of Central Florida, and I'm presenting our work Time Balance, Temporally Invariant and Temporally Distinctive Video Representation for Semi-Supervised Action Recognition. This work is done with Mamshad Rizvi, Dr. Chen Chen, and Dr. Mubarak Shah. Our work proposes a unique dual teacher and student framework for semi-supervised action recognition. Each teacher is pre-trained with different type of video self-supervised representation, that is temporally invariant representation and temporally distinctive representation. First, input clip is processed through both teachers. Their prediction is combined through the proposed reweighting strategy, and this combined prediction is used to provide unlabeled supervision to the student. And whenever labels are available, student also receives supervision from there as well. For reweighting strategy, we compute an instant similarity score from temporal self-similarity matrix from distinctive and invariant teachers. If the score is high, we put more weightage to the invariant teacher. If score is low, we put more weightage to the distinctive teacher. Our method achieves state-of-the-art results on 3 benchmark datasets. We'll be going through a number of key topics. First, we'll discuss the motivation behind our work, why we are focusing on semi-supervised learning, and how is that important in context of video data. Then we will delve into the concepts of temporal invariance and temporal distinctiveness and how is that relevant to our framework. So this leads to our main proposition, that is time balanced framework. Next, we'll explain the temporal similarity based reweighting strategy. We'll present our experiment. And finally, we'll wrap up with the conclusion summarizing the main takeaways of this work. Semi-supervised learning deals with the problem of enhancing performance on small-scale labeled dataset, leveraging the large-scale unlabeled dataset. So semi-supervised learning is more crucial for the video datasets, particularly because of their higher cost of annotation compared to images. When compared to images, videos provide an additional temporal dimension. So this can be exploited to leverage unlabeled data more effectively, and which makes this problem more interesting. Prior works have been heavily relied on the two-stream based network, for example RGB plus optical flow or RGB plus temporal gradients, or two-stream based playback like fast playback and slow playback. So we can say that prior works have very input specific inductive bias, and we know that like pre-processing all the optical flow or temporal gradients require a lot of computation. For example, computing like optical flow on kinetics data takes about a week. So, and another thing is that prior works have not systematically leveraged the self-supervised video representation. Now let's talk about the types of the video self-supervised representation. One could be simple extension of SimCLR kind of framework for videos, which is like taking 2 clips out of a video and taking as a positive while repelling the clips of the other videos. So this kind of contrastive loss would encourage 2 clips of the same video to have same representation. So in a way, it is like promoting temporal invariance, or we can call it temporal invariant representation. Another kind of contrastive loss would contrast the timestamp of the same video. And so this kind of contrastive loss would encourage 2 clips of the same video to have different representation. So, or we can say temporal distinctive representation. In order to understand the behavior of temporally invariant and temporal distinctive teacher, we take those teachers, fine-tune with a limited amount of data, and plot the performance difference across the UCF11 classes. So on the left side, we can see the classes which are like more complex or which has many sub-actions. So in those classes, we can see clips from the same videos are also visually very different. And clearly, a temporally distinctive teacher is performing better there by a significant margin of 30% to 10%. And on the right side, we see the actions are more kind of atomic or repetitive actions. And on those actions, temporally invariant teachers is performing better. So let's dive into our framework. So our framework is a dual teacher and student framework. Let's start from a clip of a video. And so this clip is given to both teachers and we obtain prediction out of that. So these both teachers are pre-trained in self-supervised way with different type of self-supervised training, and they are fine-tuned with limited label data. So once we obtain the prediction from the teachers, the prediction is combined with the proposed reweighting strategy, and this combined prediction is used to provide unlabeled supervision to the student using L2 loss or some standard distillation loss. And whenever label is available, we also provide supervision from there as well. So overall loss would look the weighted sum of supervised loss and unsupervised loss. Let's talk about the proposed reweighting strategy. So from a video, a bunch of consecutive clips are obtained, and pass through the temporally-invariant and temporal-distinctive teacher to obtain the self-supervised representation. And from this representation, we obtain our temporal self-similarity matrix using cosine distance for both teachers and average out those metrics to obtain average matrix and take the sum of non-diagonal element to obtain our instant similarity score. If the similarity score is high, then we give more weightage to the invariant teacher, and if it's low, then we give more weightage to the distinctive teacher. Now let's take a look at the illustration of teacher reweighting. For this fencing action, if we compute temporal self-similarity of invariant and distinctive teacher and compute instant similarity score, then it produces high score. For this javelin throw, it results into relatively low score. So we can observe that since this fencing action was atomic and repetitive, it produces high similarity score, so we end up giving more weightage to the invariant teacher. And for this javelin throw, since it was bit complex action, it results into low similarity score, and we end up giving more weight to the distinctive teacher. Following the prior works, we also show results on 3 benchmarks, UCF101, HMDB, and Kinetics 400 at different level of labeled data. First, we show results on semi-supervised baselines, then video-specific semi-supervised methods, self-supervised baselines, and our method significantly outperforms all of the prior works. And the same observation also holds for the 3D Resonant 50 architecture as well. For the ablation, we evaluate student model which is fine-tuned on 5% or 20% limited label data of UCF101, starting with the random initialization baseline. If we add invariant or distinctive teacher, both improves the performance. However, adding both teachers, it significantly improves the performance, which shows the complementary benefits of the invariant and distinctive teachers. However, adding reweighting strategy, it performs the best. For the dual teacher pipeline, we evaluate various pairs of teachers, for example, invariant teacher or distinctive teacher, but we see a clear difference in performance while adding the opposite kind of teachers, so which shows again the complementary benefit of temporally invariant and temporal distinctive teachers. We also study student initialization from the various video self-supervised methods like TCRR, CVRL, temporal transform, or video clip order prediction. In the initial epochs of the semi-supervised training, we see that self-supervised method, which is powerful, performs better. However, training for longer, the performance difference diminishes. To summarize this, we propose TimeBalance, a teacher-student framework for semi-supervised action recognition, where we leverage the unlabeled video using the complementary strengths of temporally invariant and temporally distinctive self-supervised video representations. And we achieve state-of-the-art on the 3 benchmarks, UCF101, HMDB 51, and Kinetics 400.